Okay, so let's move on to our next speaker, Deva Ramanan. Deva is an associate professor at Robotics Institute at CMU and a principal scientist at Argo AI. Prior to joining CMU, he was associate professor at UC Irvine. His research interests are computer vision and machine learning with a focus on visual recognition. He was awarded the David Marr Prize in 2009, the Particle VOC Lifetime Achievement Prize in 2010, NSF Career Award in 2010, and UCI Chancellor's Award for Excellence in Undergraduate Research in 2011, the PAMI Young Researcher Award in 2012, one of Popular Science Brilliant 10 Researchers in 2012, and the LeGrant-Higgins Prize in 2018 for fundamental contribution in computer vision. He is on the editorial board of International Journal of Computer Vision and is associate editor for PAMI. He regularly serves as a senior program committee member for CVPR, ICCV, and ECCV. He served as a program chair for CVPR 2018. He also regularly serves on NSF panels for computer vision and machine learning. Deva is one of the authors of very popular dataset Microsoft Cocoa. He has published many influential papers on object detection, face detection, object tracking, activity detection, and so on. So next, let's welcome Deva to give us a talk.
Okay, thank you for the gracious introduction. Can you hear me?
Yes, I can hear you.
Okay, great. All right. Okay, so I will be talking about learning to understand the geometry and motion of dynamic scenes. This is very much work led by Gengshen Yang, who'll be presenting a part of this, some of this work at a talk on Tuesday, and then Pei-Yin as well, who've collaborated with Gengshen on 1 or 2 projects. Okay, so first some setup. I guess I don't really have to motivate why we care about scene geometry given this workshop. I will say that for my own self, it was a bit of a realization that I've tended to work historically more on high-level recognition problems, like object detection or activity recognition. And then in the time I've spent looking at perception for autonomy, it becomes very painfully obvious to me that the crucial question seems to be much more about geometry, of understanding what's out there in the world and how we can navigate and interact with it, rather than, let's say, naming it. The canonical example I give is if a trash can falls on the street and a bunch of debris comes out, I probably don't have detectors for every piece of garbage that's in there, but it's much more important rather than naming the garbage, just to know geometrically what's there and how it's moving and rolling around. So I think of it as somehow, this to me is much more open world recognition, which I think is going to be a crucial part of actually getting autonomy to work. So what are some particular challenges that may or may not be emphasized? So one thing that wasn't clear to me is that I think there's a huge difference between understanding the geometry of a static world and understanding the geometry of a dynamic world. And one of the really sort of scary cases is when let's say people walk out from behind an occluded car. Like here's an example. So what's happening here is that the geometry of the world is actually changing quite fast, and it's quite fast and non-continuous because of occlusions. And so that means you must be able to rapidly figure out dynamic changes of the scene. And that's really hard, because if you want to rapidly react to dynamic changes of the scene, then how do you know your estimates aren't just flickering over time? So maybe you want to reduce flickering by enforcing some temporal consistency by smoothing over time. But then if you do that, you reduce your ability to react to dynamic changes. So that to me seems like a fundamentally hard challenge. The other big challenge is that, especially as we move toward deep neural approaches for these solutions, to what degree are we kind of hallucinating the geometry we expect to see, versus to what degree are we actually measuring the geometry that the data is telling us? And the reason why that distinction is so important is that I think that's why LiDAR is such a powerful tool, because it's purely measurement based. It's not prior based. And so even if you have prior expectations that don't jive with what you're seeing, the data is golden. It tells you that there's something there, even though you didn't expect to see it. And then finally, I think it's become super important to not just the way that we measure accuracy and success. It's not just, for these safety critical applications, I've heard before that we need to get to 100% accuracy or 99.999% accuracy. And personally, I think that we're not going to get there, but I think what we can shoot for is graceful degradation. So that when we do make a mistake, when we misestimate the geometry of the world, we do so in a graceful way. And so these kinds of challenges, one of the things that we've been thinking about as a philosophy for addressing them is, well, how do biological agents, how are they able to navigate in a world? Flies and rodents can seemingly move around in a dynamic world that's changing and understand what's happening. And furthermore, there's various human vision experiments that suggest that humans are actually technically not that accurate in estimating 3D metric geometry. I don't really know the number of millimeters to that corner of a wall, but it's kind of remarkable that if I don't know that, how am I able to navigate something moving at 60 miles an hour? So I'm gonna talk about some representations and approaches that are inspired by how we think humans might be doing it. Okay. So first, I want to sort of start by motivating a lot of the low-level analysis of geometric estimation, such as like estimating stereo disparities and reconstructing the world from that, or even understanding how things move over time, local optical flow. The heartbeat of all of those approaches is really correspondence. In terms of stereo, if I have one point on the left image and I search over a scan line of possible matches in the right image, if I can find the right one, that tells me the disparity of the depth. And for optical flow, I'm basically doing the same thing, except that now instead of searching over a 1D line, I'm searching over a 2D window. So I wanted to talk about some approaches that we've been pursuing for kind of neural modifications of these architectures that I think are kind of rapidly advancing the state of the art. Okay, so in order to sort of describe the approaches, I want to first just recall how would we classically do this? If I was doing stereo or optical flow, what I would first do is extract local features at every pixel, XY pixel. Then a lot of approaches classically compute what's called a cost volume, which is for every pixel in the left image, I search for possible candidates in the right image. And then I compute the match score or the match cost of corresponding this pixel with this pixel. And I'll store this essentially in a 4D array. That's X, Y, Y by U by V, where the UV is the search window. And if you have this cost volume, a naive approach might say for every XY pixel, just find the minimum cost UV offset. And that's sort of the simple way of finding optical flow vectors. And if you want to be, essentially, there's this huge body of work of saying if you do that, it'll be too noisy and you'll suffer from aperture problems. So then we instead resort to sort of sophisticated methods for regularizing the optical flow or the stereo disparity so that nearby pixels have similar flow vectors or similar disparities. And one more thing I want to point out is, even though this is very classic, one really cool thing about this cost volume perspective is that essentially it enumerates possible interpretations of the geometric world. Does this correspond? Does this correspond? Does this correspond? And that gives you one kind of estimate of uncertainty, because you can look at the best scoring match and you can look at the score of the next best scoring match. And depending upon what margin you get or how far away those are, you can use that as a way of calibrating. If there's multiple good scoring matches, then maybe you shouldn't be certain about your correspondence. If you have like a featureless wall that you can't match well. So these classic approaches, even though simplistic, actually do something really nice. And a lot of contemporary approaches, including things like FlowNet and FlowNet 2.0, what they do is they'll start with this cost volume. They first extract local features by computing some deep embedding, construct this cost volume. But then importantly, they'll take this cost volume, which sort of naturally is this 4D structure, and they'll collapse it into a 2D multi-channel data structure, a 2D multi-channel image. And so now subsequent processing of this data structure, you can just use 2D filters. And the reason for doing this is that this fits in really nicely into all of our existing, convolutional frameworks. And at least what we found is that instead, if you keep this thing as a truly high dimensional volume, as a 4D tensor, you can get much better accuracy, much more better estimates of uncertainty, and even faster training and better generalization. So we have a paper this past NeurIPS that talks about using these techniques for flow, and then this last CVPR on using it for stereo. So let me just sort of give a little bit of high-level intuition of what are the tricks involved to getting this to work. So one is kind of an obvious one. A lot of these are obvious, and that is all of the standard kind of insights we have for 2D convolution, they apply for 4D convolution. So if we're going to train residual networks, that sort of you add a delta to the previous estimate. If you're going to train a UNet architecture or spatial pyramid pooling, there's essentially very natural 4D equivalents of all this. That if you do, all of a sudden 4D processing becomes much more efficient. And this was one kind of important trick that it's kind of a cute mathematical observation that was also useful to getting this to actually work in current kind of neural toolboxes. And that is, if you have a 4D data structure and you want to convolve with a 4D filter, because those aren't native, such operations aren't natively supported or aren't that efficient, what you can do is you can take your 4D filter and do a low rank approximation of it as two filters. One that's 2D, let's say in the spatial XY dimension, and the other one that is, I guess, 2D in the UV dimension. It's hard to show that here. And what that means is you can essentially do 4D volumetric processing with a bunch of 2D multi-channel convolutions, but you have to reshape your data structure so that the batch dimension is different every time. There's a little bit of work involved, but it turns out you can just do this using current routines. And I just wanted to stress that this is a little counterintuitive. This turns out to be much, much more faster and space efficient than actually treating this thing as a raw multi-channel 2D image. Because if you treat this as a raw multi-channel 2D image, you take all your UV dimensions and you flatten them out, and you have to train filters that have a huge number of channels because across every possible UV offset. So if you compare to the sort of FlowNet style architectures, this is 40x fewer flops, and it's almost 3,000 times fewer parameters, because we're essentially, the filters that we're using are really small, like 3x3x3 filters, instead of filters that go, I don't know the exact dimension, 128 or bigger in terms of number of channels. And finally, another sort of final trick that seemed to be quite useful is this notion of multi-channel cost volumes. And so the idea here is also pretty simple. Pretend that at every pixel, instead of extracting one feature or one embedding, you extracted three features, three embeddings, denoted by the colors yellow, red, and blue. And now what I'm going to do is I'm just going to construct three different cost volumes. So red, yellow, red, and blue. But now I'm going to treat these k different features or k different cost volumes. I'm going to treat the k as the channel dimension. So what this will construct is a h by w by u by v by k, a 5-dimensional array. But I'm going to think about that as a 4-dimensional multi-channel array. And the advantage of doing this is, the hope is that these different feature embeddings capture some different notions of appearance. So maybe one is like a texture appearance, and the other is a color appearance. So the yellow cost volume tells you how well two things match in terms of texture. The blue cost volume tells you how much they match in terms of color. And now when you do volumetric filtering on top of this, those volumetric filters have access to texture similarity and color similarity. So it's much less of a bottleneck. If you just use a cost volume, you're squeezing everything down to one number that says how well this pixel matches with this pixel. But now we have k numbers that sort of tell us how well this pixel matches with this, and that can give a much richer description of matching. And then finally, because we keep with everything in a cost volume, we can still spit out a result that's a cost volume. That is still h by w by u by v. And then we take a min or a soft min or a soft max around that final UV dimension. And so now we still get uncertainty for free, because we can look at the entropy of that soft min, or we can look at the next highest scoring one that's not the actual min to get a notion of how certain we are. Okay, so it turns out you can build methods for doing this. And here's sort of some examples on synthetic data where we have ground truths and tell. Below is some examples on sort of autonomous driving data from, driving data from Kitty. And if you actually push through the numbers, this produces state-of-the-art or very close to state-of-the-art in almost all dimensions. And so the top table kind of just shows a bunch of numbers. It turns out in the flow world, there's this distinction of you can certain flow methods, if you train purely on synthetic, that's one domain of evaluation. And there's another sort of setup where you get to fine tune on real flow data, which is hard to get. And in both those settings, state of the art. When this was published, so I imagine there's new stuff coming up in CVPR as the rapid pace we live in. But I will say that it seems like even newer methods are now also keeping with this true volumetric approach, because it seems like that is useful. And perhaps one thing that really stuck with me is that when you look at this volumetric approach, the training time is dramatically different than when you train normal networks. So I'm showing that in the bottom left table and the bottom right graph. So essentially this thing converges to state-of-the-art accuracy after 80,000 iterations versus other methods that can easily take an order of magnitude more, 20 times longer. So this was something anecdotally that we saw, that it seems like if you architect things correctly, it'll train easier, it'll converge faster, and it'll tend to generalize more. And so what I mean by that is, I'll go to the next slide. One of the cool parts about actually having an explicit UV sort of offset dimension in addition to your spatial dimension is that we can actually train with one UV window and then test on a different size UV window. So in the extreme setting, and this is kind of neat, you can train a stereo network and you can test it on optical flow, because you're essentially just changing the dimensions over which you search over. Or you can train a flow network and test it on stereo. And one of the reasons that's nice is because it's actually hard to get lots of training ground truth for optical flow. And it's much easier to get training ground truth for stereo, because you can use a sensor like active illumination, like LiDAR or Kinect. So that means, so in fact, we can actually train pretty competitive networks that have never seen any real flow training examples. It's purely synthetic data plus real stereo data. And that sort of shows the ability of this thing to kind of generalize. We've also done cases where you can train it on very small offset windows, but then run it on larger windows for sort of ease of training. So you get to kind of speed up training a little bit, but that it seems like there's an element of generalization you get by using this cost volume structure. Okay, and so one example of this was actually trying to do this for stereo. And so the previous results I've sort of shown for flow. And for stereo, we actually started with a slightly different motivation. Our goal wasn't to explore cost volumes, but it was rather to explore this sort of targeted hypothesis, which is what happens if, is it possible that because geometry is so important for navigation, is it possible to replace active sensors like LiDAR with stereo? And for a long time, I thought that this was not possible because of baselines. Because if you really want to get accurate geometry for something far away, because of the way triangulation works, you need to have very far away baselines between your cameras. The closer the cameras are, the kind of more sensitive it is to the actual far away depths. And you can kind of compute this very easily using error analysis. So that the error in the Z and the depth that's estimated grows quadratically with the depth, and then also with the baseline and the focal length B and F below. But one thing that I didn't quite realize until someone pointed this out to me is that it's not really the baseline in terms of millimeters between the two cameras. It's really the baseline in terms of pixels between the two cameras. So if you just increase the resolution of the two images, you're effectively increasing the baseline count. Now you can grow to a baseline of 400 pixels from 200 pixels without actually changing the physical geometry, just getting higher resolution cameras. So what's neat about that is we know we're getting higher resolution cameras in our back pocket every year. That's a very scalable sensor. So what we really started to attack this problem with is what happens if we wanted to do very high res stereo to get accurate geometry far off. And the essential thing we ran into was memory constraints. Because if you're trying to build a cost volume, even with a 1D scan line for a huge number of pixels, this thing becomes too big to actually sort of run. So number one, you have memory constraints, and you also have latency constraints. And the other important part about doing this for navigation is that because the world changes fast, you have to estimate what's happening in the world quickly and then move on to the next frame. So you can't afford to spend a lot of time processing a single frame. So roughly speaking, one barometer might be a LiDAR sensor, which processes a sweep every 100 milliseconds. So there you have a snapshot of the world every 100 milliseconds. So if your model takes longer than that, somehow it's, maybe you should just use a LiDAR sensor instead. So the way that the way that we tried to address this computational burden, both in terms of memory and in terms of latency, was essentially also embracing a classic pipeline of course define. And so hopefully we all know of things like optical flow, Lucas Canade, course define is a very classic way of dealing with high resolution correspondence estimation. But one of the classic challenges in course define is that essentially the trick is if you have two high resolution images and you're trying to estimate correspondences, well, the first thing you do is just subsample, make them two low resolution images, and then estimate correspondences, and then use that to kind of initialize correspondences at the finer resolution. But the problem is that it's a well-known limitation is that if you have something small that's moving far between the two images, then when you look at the low resolution image, it becomes blurred out. You don't even see that small thing. And so you don't initialize a good correspondence from which you can then fine tune it at the fine layer. So it's fundamentally hard to find small, skinny things that are moving far. So an example of this in the autonomous setting is that if you have a pole that's actually close to you, that's really skinny, but it actually has a huge disparity between the left and right image. And in the blurred version of the image, you might not even see the pole, so you don't sort of initialize the right correspondence. The one kind of cool trick about one way to sort of set this up is that you can basically separate out the course define processing in terms of the feature extraction and the cost volume processing. So the feature extraction, we just do what we normally do. You just run it through a network at the high resolution, image. But importantly, when we construct features from a network, our features are inherently multi-scale. There was this old work from Barath Harihan of hypercolumns. I can extract the descriptor, which extracts features from multiple levels of a convolutional neural net. What I can do then is I can take those features, which are inherently multi-scale by extracting them from different layers of a network, and I can first construct a coarse cost volume. So that represents the green box in the middle there. And by estimating a coarse cost volume, I can estimate coarse matches between geometry. And I can use those to initialize a finer scale cost volume. So we think this is kind of neat in the sense of you can apply this coarse defined processing just at the cost volume at the cost volume stage. And so sometimes this is also known as a multi-grid approach. And it's interesting because the initial processing of the image, I oftentimes think of as fine to coarse. Initial layers of a network first do very local filters and you get larger and larger, bigger receptive fields. So it's this way of splitting things up that allows you to then manage compute. And then a final kind of, it seems like a very trivial observation, but I haven't quite seen it made, is that if you do coarse define, another huge benefit is that once you estimate coarse matches, that actually gives you coarse disparity, you can just report those and then while you're computing the fine scale disparity. So this has a very natural anytime component to it. So before you're done processing the network, you can get a rough estimate of geometry at 120 milliseconds. And that can tell you, roughly speaking, if you're a navigating agent, should you slow down, should you pause, because something could be there, even though it'll take you another half a second to precisely figure out the geometry of what's there. And if you wait long enough, you will see that. So that's another added benefit of building in these coarse defined structures, which is actually somewhat straightforward in this cost volume perspective. Okay, and so because of that, we have, compared to on the x-axis is time in a logarithmic scale. On the y-axis is error, so you want to be at the bottom and on the left. And so that's that lone blue point, that pentagon is actually us. So the next best method takes quite a bit longer to compute. So if you actually were to draw that dotted line, which kind of represents real-time methods, we're quite a bit more accurate than previous methods on Middlebury. So this is certainly a highly benchmarked stereo data set. And a couple more tricks of, so we're hoping this notion of like high-res stereo could be sort of a thing that people work on, and we hope people work on, because it seems like it has the potential to rival other much more expensive and sometimes hard to work with sensors. So number one, there's not much high-res benchmark data for stereo available. Middlebury, I think, has 15 high-res images, but that is rapidly changing. And one of the reasons it's changing is because autonomous vehicle companies get high-res data that comes annotated with LiDARs all the time. So this is something that I think is, we're releasing some, but other folks are releasing some as well. So pretty soon we'll have a huge amount of this high-res stereo data, I think is sort of an interesting problem to work on. And one more kind of subtlety that we didn't realize until we worked on it is that one more challenge in the high-res stereo world is because you're working with such high-resolution pixel images, you now have to be very precise in terms of your rectification. Because if you have a slight error, you might actually match to a pixel on a different scan line. Before it didn't matter because we didn't have that many scan lines, but now you have thousands of scan lines because you have a megapixel image. So one of the things that actually helped performance was to add in noisy rectification during training. And we did this actually using synthetic training data. So we grabbed stereo images from renderings from Carla, and we perturbed intentionally. It's almost like data augmentation, but instead of in the image space, it's actually in the camera geometry space. And by training on that, this becomes actually so that the true match is not on the scan line, it actually lies off. Then the final networks actually become much more robust, which I think needs to happen when you're working at this high resolution. Okay, so that was sort of a quick discussion of multi-view sort of geometry approaches. And so now I wanted to sort of dive into actually one of the papers that Gengchen will be presenting in a couple of days in a talk. And so here, this really stemmed from the motion of, it stemmed from the observation that always kind of bugged me, which is, it seems like from a biological perspective, we don't need precise geometry. We don't need lasers to shoot off and bounce off objects. But if that's the case, what do we actually use in terms of being able to navigate with the geometric scene around us? And this is no surprise, it's actually well known, or it's very strongly posited that we use cues such as time to contact or looming, where this is a figure from J.J. Gibson's influential early work that pointed out that divergence of flow gives you a clue as if you're approaching something or not. Essentially, things that move closer to you will get bigger, and so that's a very big clue as to a change in depth. So we wanted to see, can we build models and networks that employ that kind of intuition as a way of understanding dynamic scene changes. So the title of this paper is actually, it almost sort of summarizes the whole approach. But essentially, the observation is that, let's say the input is 2D flow, and I just talked about we use our own 2D flow network, but of course you can use anything. And the goal is to actually produce some estimate of what's dynamically changing the scene. And I'm going to argue that a reasonable output here is 3D scene flow. So there's different ways of encoding this. You can think about this as every pixel, I want to estimate a 3D vector that tells me how it's moving in 3D. Sometimes you're also required to estimate the starting point or the end point of the vector. So that can be the depth of it. But in some sense, that's not going to be the focus of what we're going to estimate, although we'll estimate that as well. And the crucial observation is what we're going to do is we're going to introduce this new quantity, this new representation that we're going to call optical expansion. That at every pixel we're going to estimate from a pair of frames, is it getting bigger or smaller? And we're going to use that to gauge, is that point moving closer to us or not? And it turns out that if estimating things are getting bigger or smaller, that we can do. We actually have pretty good tools for doing that, but we have to repurpose kind of existing flow networks. Okay, so here's a little bit of sort of theory to whet your appetite. So imagine it's a top-down view of an image plane. The camera center is the gray point. And now we have some flow vector, which we can't see because we're the top-down view of the image plane, but we have the two blue points. And now we can ask ourselves, here's a 2D flow vector. What are the 3D interpretations of the world that could correspond to this 2D flow? And basically for the source point and target point, there's a ray that pops out. And we just don't know where in 3D the source 3D element was on the ray and where in 3D the target 3D element was on the target ray. So there's actually 2 degrees of freedom that that are unknown whenever someone gives us a flow map in terms of understanding what's happening in 3D. And so the simple observation we make is that in addition to the flow map, if we can estimate if the point is getting bigger or smaller, that actually tells us the relative change in depth. And you can look to the paper for precisely what conditions this holds, but it kind of follows your intuition. Essentially, like perspective projection equations will show that if something gets bigger, sort of the ratio by which it gets bigger is equivalent to the ratio of the depth change, assuming that it's not rotating and not deforming. And this again is sort of well known in the psychophysics literature. Okay, and so now what we're going to do is we're going to build a network to estimate the sort of changes in scale. And what that does is that eliminates 1 degree of freedom. So now we actually know, this is kind of neat, we now know the true 3D orientation of that point, how it's moving in 3D. We just don't know if it's really a far away point that's moving far or a close by point that's moving a little bit. And then hopefully this picture shows you that if something else told us either the true depth of the source point or the target point, it would eliminate that last degree of freedom. And this is actually the pipeline that we talk about, of sort of upgrading from 2D flow to 3D scene flow. Okay, and there's sort of a network for sort of estimating these things, and you can kind of go to Genshin's talk for more details. But essentially, you start with flow. We first get an analytic we analytically compute the divergence of the flow. So that's a sort of just no learning involved, and that's what you're seeing in the middles in the middle image. What's kind of cool about that middle image is that it looks like it's showing you 3D, but it's not. It's totally 2D estimates. It's just showing you what gets bigger. In fact, you can see, if you were to look at some of the more examples, that sometimes you see the one example where the car is moving toward us. It's not that there's nothing else rigid in the scene. Everything else is rigid in the scene, but everything else is moving away from us. So that's why that looks really dark. So this is actually a visualization of, in some ways, is time to contact. So bright things are things that we're going to hit sooner. So we can compute optical expansion, but we said before that that doesn't exactly correspond to changes in depth because of various assumptions that are made. Things have to be orthographic and non-deforming. So then we train a residual network to actually compute true changes in depth from that. And then finally, we take that, and that gives us the true orientation and direction of 3D movement. And we add to that something else that will tell us either the source or target depth, and that gives us the full 3D flow vector. Right. Oh, and for training, we can train on using normal scene flow data sets, but what's also cool about optical expansion is that there's a bunch of pretty exciting methods for self-supervised learning of optical flow that basically says if you have an image and you predict a flow, and I can push all the pixels forward by the flow, and I can compare it to the measured image frame in the next time instant. I can use the error, the photometric error between that as a signal for learning. You can use the exact same thing for optical expansion. So it turns out we can also train this in a self-supervised fashion on large amounts of data. And so we show various applications of this. So one is monocular scene flow estimation, actually trying to, from just a pair of sequential images, estimating the 3D scene flow. So there we end up using some other off-the-shelf monocular depth estimation network to provide us that 1 degree of freedom that our method can't resolve. We also tried stereo-based scene flow, which is also another benchmark. There, what's nice is we can just use some off-the-shelf stereo network to provide us that initial source 3D point. And in both of these methods, I believe we're now state-of-the-art. And I won't get into the details here. Here I'll show I think a really cool application that I didn't quite realize until Gengshin brought it up, which is there's this problem that's been defined called LiDAR scene flow or point scene flow, which is if you're given LiDAR sequences from 2 frames, can you estimate how one set of points, where those points will move to in the next frame? And usually this requires estimating, usually the input is 2 sets of LiDAR frames. What's kind of cool here is you can take one LiDAR frame, and because LiDAR is a continuous, essentially a rolling shutter sensor, it takes 100 milliseconds to revolve around and grab a frame. In order to get 2 sweeps of LiDAR, you actually have to wait for 400 milliseconds. What you can do here is the second you get 1 LiDAR sweep, you can take a camera or a pair of camera images instantly and use that with the techniques we talked about to actually compute a LiDAR scene flow where you expect these points to move before you even get the second LiDAR sweep, because cameras can be triggered much faster than LiDARs can be. So it turns out that these methods are much more accurate than the methods that actually require 2 LiDAR sweeps. So the error is in the last column. There's been other methods that recently use stereo as well, but importantly, what we're talking about just requires not stereo, but a single camera with, but still a pair of images. And we can basically get near the accuracy of stereo and still beating out a whole bunch of stereo baselines as well. So it's a sort of interesting problem of using kind of multimodality where you're getting not just higher accuracy, but also sort of increased temporal resolution. You don't have to wait for these sensors as much using this approach. Oh, and another Sorry here. Oh, and another application. I think this is very much synergizes with what Katerina was saying, is that using these methods for finding objects that move, so moving object discovery. So now, instead of just using 2D motion, we can use 3D motion as extracted using this this upgraded scene flow. And here's an example of someone riding an e-scooter, where we don't really have detectors for e-scooters, but if you use motion-based object discovery, you can discover that someone is interacting with this object. And finally, this goes back to just classic structure for motion. It turns out that you can still use these ideas of optical expansion to improve the accuracy of structure for motion, and we specifically look at it in the context of two-frame structure for motion, which is a pretty difficult setting. But if we go back to this notion, if I want to estimate the geometry of a dynamically evolving world, then you should be able to do it in sort of very quick, hopefully over very quick sort of sensor readings. You can compare it to other methods like CalMap, which is a very tried and tested method for structure for motion, and then monodepth, which is a single frame depth estimation method. And ours compares quite well across these. We evaluated on some benchmarks for structure for motion. Okay. So sort of the summary for this part is there seems to be, we can think of expansion, which is this very classic biologically inspired cue, as a tool for upgrading 2D motion estimates to 3D motion estimates. And then because we know that optical flows, it's used in so many kind of pipelines. And if you want to do action and activity recognition, many methods, two-stream methods use flow. Or hopefully we want to convince folks that maybe instead of just using optical flow, you can just append that with another channel, optical expansion, which is almost as reliable to extract. And now you can get a little bit more sort of 3D estimates of what's happening for your downstream application. And I'll just conclude with like a little taster of an older piece of work, but I think is still interesting. So finally, all of these methods that I talked about were really multi-view methods that either require 2 views or 2 frames at least. And at some level, I do think that it's interesting and worthwhile to explore single frame methods, like purely monocular depth estimation. And I think there's a couple of really exciting papers that are coming out in CVPR that suggest that the accuracy of this is increasing quite a bit. The one thing that I want to stress is that if you look at some of these attempts, there's still some scary things that happen. So here's a method. Here's an example of taking a state-of-the-art monocular depth estimation network. When you look at things that are slightly unusual, like trucks, you'll often see really bad, unreliable depth estimates. And this, of course, is scary if you're going to use this to navigate, because you're misestimating where free space is. So I think what's super important in these settings is to again somehow structure the network in a way where we can understand what it's very sure about and what it's not sure about. This notion of degrading gracefully when there's a mistake. And so we have this old piece of work that tries to say, okay, how can we use these networks to infer not just fixed depth, but sort of a distribution over depth, so we can tell where is the distribution really confident and where is it really diffuse. And there's various ways of doing this with Bayesian neural networks that sometimes are pretty expensive, and I think might be hard to actually pull off in a real-time navigation setting. But the approach that we take is actually inspired by this cost volume philosophy. What we do is we essentially just discretize possible depths in this log polar fashion. And then we train something that predicts sort of a confidence at each depth. And so what that allows us to do is, even though we can pick the most confident depth, we can see, is there another depth that's equally as confident, to sort of let the network tell us, is there actually multiple outputs that it might have been happy with. And although it's pretty simple, we found this compares quite favorably when you look at evaluations that score the ability not just to produce the best depth, but to make sure that you also are confident in the depth that you're responding with. And I think that those are somewhat less common evaluations, but I think those are super important if we're going to think about using these methods for safety critical things like navigation. And here's sort of a fun example of the top result with estimating depth in the middle, and then below is an estimate of entropy. So sort of looking at how certain is it about all the possible depths it could be. And here's one application that's sort of tied to the workshop theme of kind of map building, which is we take all these estimated depths and we stitch them together. But importantly, we only stitch them together and align them using confidence depth estimates. So we just threshold depth estimates that have low entropy and ignore them. And the subset of confident things, then we align. we can actually build geometric maps just from monocular depth estimation methods that are kind of close to the ones you can get from a LiDAR sensor. Maybe we'll sort of see this in just a second. So I think this is an example of where things have been thresholded to not take advantage of depth estimates that we're uncertain about. And the very end will sort of show 3 different examples here. Yeah. So LiDAR is the top one, and then we have a version of ours that uses this uncertainty reasoning. Okay, so that was, I'll sort of conclude here. So what are the morals that I hope you can kind of walk away with? So one is this notion of discretizing possible geometric interpretations of the world, either through a cost volume or the simple sort of log polar discretization I quickly went over at the very end. That seems to be a very useful way to implicitly encode uncertainty and reliability. The other sort of take-home message is that a lot of classic tools for geometric processing really make use of spatial data structures like volumes and cost volumes. And even though it seems like we're using them in a lot of our network architectures, I argue that we're not, that oftentimes we take cost volumes and we smush them into 2D multi-channel things just so we can use our normal tools on them. But if we embrace the fact that they're actually volumetric, a lot of things end up being easier and more robust and generalizable. And finally, if we think about, the final goal is to, in some sense, not just estimate the geometry of the rigid world, but to really estimate the geometry of a dynamic world and estimate correspondences. So that ultimately seems like a 3D scene flow problem. And we can use sort of 2D flow estimates combined with expansion to hopefully get us there. Okay, I'll conclude there. Thanks.
Okay, thank you so much. Thank you for the interesting talk. I think next I'll ask a few questions for our audience. So here's a question in terms of deal with the memory constraints. So are there other possible ways other than multi-scale feature methods?
Yeah, I see. Okay, so what are so what are ways to deal with memory constraints? I guess my initial thought would be multi-scalar course defined. So I guess the memory constraint we run out against is we're enumerating possible matches. So if we have really high resolution data, there's a bunch of possible pixels that can match. But we know that the simplest way of fixing that is don't do high resolution data. And then you just kind of intuitively, I always end up back at these kind of course defined multi-scale methods. Historically, it feels like that has helped for vision quite a bit. But what I find intriguing is that we know that in the past they have certain problems like this example of something small that moves far. But maybe we can architect our neural solutions to compensate for those problems.
Okay, maybe another question is related to this. So you mentioned the cost to find methods. So on smaller or coarse scale, so we may have some errors for the optical flow disparity. Do you have good ways to correct those errors along the way of upscaling the features?
Yeah, that's a great question. We've actually thought a little bit about that. So, I mean, another problem, of course, to find is that once you make a mistake, then you're kind of stuck as you go down to the fine level. And another version of what you could be saying is that at the fine level, maybe you can realize you made a mistake earlier and you want to correct it. So that suggests to me almost something else, something that's a bit more bottom up and top down, where you can use some fine scale estimates to help refine what you think the course estimate should be. One thing that that I hinted at that you could do is this notion of like on-demand searching. So you can choose what are the pixels you want to try to evaluate. And you can do that based upon initial things that you've looked at. So in theory, if by searching over some pixels at the fine resolution, you realize I actually want to search more around this region that I didn't get a chance to search through at my current sort of course boundary, then you can dynamically change. So that's something that I feel like by having a method that somehow factorizes the search space of which you're searching over correspondence, and then the other stuff, the feature extraction plus the convolutional processing, And the ability to sort of dynamically change where you're going to searching, that could be one way of getting sort of fine scale information to help sort of give feedback for the core scale cues.
Okay, yeah, we have another question from our organizer.
Thank you very much for the great talk. Very much enjoyed it. It's going in the direction of course define and the memory problems. I'm wondering whether part of the problems that we're seeing comes from trying to shoehorn everything into a dense data structure, where the sum of those signals might actually be sparse.
Yeah, and that's a great question. So I guess, we're sort of somehow handcuffed by GPU land, where we know that sort of things, we can do stuff sort of naturally in parallel kind of easily. And they're oftentimes are not nicely suited for sparse. Like in many ways, I guess, like the other view, like a lot of the classic pipelines do operate in a much more sparse way. Start with interest points and then try to match those. It's a great question to think about how better to kind of do this. I will say that one of the ways in which we end up using this output is like we're essentially computing dense correspondences, but then we threshold based on uncertainty, and then we actually kind of pass that information for downstream applications. So that thresholded output, I think of as somehow like quasi-sparse. So what we actually find is that, so like traditionally interest points, the sparseness, some of it comes from the fact of, okay, because if there's a flat region, don't try to estimate correspondences there. Here, I think a lot of times we actually are able to reliably estimate correspondences on flat regions, but instead the places where we're not certain is when there's occlusions or boundaries. So we end up kind of getting more coverage than the traditional sparse method. But yeah, sometimes I was wondering, maybe there's this notion of, maybe there's an intermediate regime, this kind of like quasi-sparse or quasi-dense, where most of the things you can get, but there's some things you definitely say, I don't want to hallucinate that. I want to get other information to fill that in.
Thank you very much.
Okay, the next question, I think you have already touched a little bit about this for self-supervised learning. So can you maybe elaborate a little bit, like how do you extend the volumetric processing method to a self-supervised approach?
Yeah, so essentially you could think of the self-supervised observation is really more about the loss function rather than the actual architecture. So I didn't really talk in detail about the loss functions, but there's almost two components of the loss functions we use. So one is, if you have training data where you have ground truth optical flow or ground truth disparity, you can just add that as a loss. You want the predicted disparity or the predicted optical flow, the argmin or the softmin, you want that to have low distance, L1 distance from the true one. There's another loss function that's natural to build, which we'll call photometric loss, which is in any of these correspondence tasks, you're always given two things, and you're trying to estimate, if you estimate the correspondences correctly, then I should be able to take one image and vect it forward by the predicted correspondence maps, the flow. That produces a predicted image, and I can compare that with the measured image, either in the other stereo pair or in the next frame of its optical flow. And that gives me an error that I can backprep on. So essentially, it's the cost volume processing is a pretty natural thing that can still be used for self-supervised learning. Perhaps the more sort of subtle thing was that this notion of expansion can still be used for self-supervised learning, because one of the weird things is that like we don't have any 3D annotations in the normal sort of image sequence data that we have. So it's a little bit surprising that we can do somehow 3D-ish self-supervised learning. But it kind of is maybe a bit more straightforward to see. If all you're doing is really estimating 2D expansions of things getting bigger and smaller, that we believe we can kind of do with our kind of like 2D, sort of like our 2D flow networks. Hopefully that answers that question.
Okay, right. I think, yeah, I think this is due to the time constraint. Yeah, this is end of the talk. Thank you so much.
Okay, thank you.
Bye.